Perhaps the two most important rules in studying circuits are called Kirchhoff's rules, or possibly Kirchhoff's laws, as they're sometimes called. This video will introduce you to the two Kirchhoff's laws that we'll use in analyzing circuits, starting with Kirchhoff's junction rule. Kirchhoff's junction rule can be simplified to saying that the total current entering a junction has to be equal to the total current that's leaving a junction. To understand this, we have to know exactly what a junction is. A junction is simply a place where two or more wires meet. You can see in my diagram here, the junction is pointed out with a dot on it, but that dot's not necessary. To this junction, I have two currents coming in, labeled as I1 and I2. And so my current that's leaving the junction, labeled in this diagram as IT, is equal to the sum of I1 plus I2. The second of Kirchhoff's rules is called Kirchhoff's loop rule. That tells us that the total change in electrical energy around any closed loop in a circuit is zero. What that means is that as a charge moves around in a loop, going from its starting point and back around the circuit back to its starting point, that the amount of electrical energy that it has to remain the same, or in other words, that the change is zero. So any energy that it gains from a battery must be converted to some other form of energy as it passes through other elements in the circuit. To help us really understand Kirchhoff's loop rule, I have a diagram here showing some graphs. If I check out the diagram, the circuit diagram at the very top of this picture here, I see that as a charged particle would move through the battery from A to B, it gains electric potential energy. Another way of saying this could be that it goes through a positive voltage. Between B and C, it's just traveling through a wire. And since we assume that all wires have no resistance in this course, it remains at the same amount of energy. Then it goes through resistor R1 from C to D. That resistor is going to take that electrical energy given to the charge by the battery and convert it into some other form of energy. Therefore, the electric potential energy will decrease, as can be seen by that downward slope from C to D, right here. Then it goes through another wire, kind of in that space between the two resistors here, and so my energy remains constant. Then it goes through one last resistor. Again, more of that electrical energy is converted into some other form of energy, thermal energy typically with resistors, until it gets back to the same amount of energy that it started off with at A. I know that between E and A, it doesn't go through any other elements other than a wire, and therefore it has to have the same amount of energy at E as it did when it was at A. Here's another example of a diagram in this middle here, where this time I go from A to B and I gain energy, so we see that the energy increases. And then between B and C, I'm just going through a wire, so same amount of energy. And then when I get to point C, I have some choices in which way I want to go. I could go through this middle element, through R1 between C and F, and that energy would be converted to some other form. And then I get, again, for a closed loop, to end where I began, I'd go back toward A, and there's just a wire there, so no change in energy there. Or if when I get to C, I choose to keep going toward D, between C and D, there's no change in energy. Between D and E, we go through a resistor, so some of that energy is transformed into thermal energy. And then if I'm trying to get back to where I started, I'd be going from E, A, which means I'm just passing through a wire, so no change in energy there. Last example, this very bottom circuit, which is the most complicated of our three. Same thing, I gain energy when I go between A and B, going through that battery. Between B and C, no energy change occurs. If I go down through R1, between C and G, I go back to my starting level of energy. Or if I continue on toward D, between C and D, there's no change in energy. But then I go from D to E, and I go through a resistor, so I lose energy. Some of that energy is converted into thermal energy. And then again, between E and F, I go through another resistor. Some of that energy is once again converted to thermal energy before I get to F. And between F and A, there's only a wire, so they're at the same level of energy. We will, of course, do many more examples with this and helping us understand how we can use these graphs to understand the energy changes that occur in a circuit.